Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to learn about graphs. Graphs are a popular topic in coding interviews, but in addition to that, they're also very commonly used in software engineering to represent relationships from real life. In fact, you probably interact with graphs all the time and may not even realize it. So after we finish this introductory slide, we're really going to dive into the real-world examples and fully understand what graphs are and how they're used. So what is a graph? A graph is just a bunch of connected items, where the items are objects. So similar to linked lists and trees, where we have individual items, where they're just connected by pointers to other items in the data structure, that's exactly what we have with graphs. And we call the items in graphs nodes, or another common name for them is a vertex. And the nodes in the graph are connected by edges. So this is an edge, this is an edge, this is an edge, this is an edge. All these connections are edges. We use graphs when we want to represent networks. So we have a network of nodes here where they're either directly or indirectly connected to other items through their edges. So 1 is directly connected to 2, 3, and 4, but we could also get to 5 from 1 by following its neighbors. So with this, we can see that a graph is nonlinear. There's no predefined starting or ending point and single path through the graph. You can start at any node, and there are many paths to reach the other items. So the concept of traversing a graph is a very important topic when we deal with this data structure, and one we'll go in depth into in this module. So the edges or connections in graphs are important because they define the possible paths, but also a graph node holds data. It can hold any data actually, but here we're just using integers. This is probably the most common data type in interviews, but it could also be strings, doubles, or any other data type. But in practice, it could be an even more complex object that has many attributes and functions. And one thing to note about these nodes is that their connections work in two ways. So they're not directed. We can get from 1 to 2, and also from 2 to 1, because it doesn't tell us which way we need to walk to find the paths through this graph. However, it's possible for these paths to also be directed. So here you can go from 4 to 1, but not back from 1 to 4. You can indirectly get there by following paths, and then eventually reaching this node again. So these are two different ways to represent graphs, either directed or undirected, but this also leads us into our first real-world example. The way users and following works on Twitter is a perfect representation of a graph. The user in the graph is a node, and then when you follow someone, it creates this edge or connection. And this works in the directed manner. So you can follow someone, but it's possible that they might not follow you back. So following someone is one way. You can follow them, and then it's possible that they could follow you back to create this bidirectional relationship, or it could just work in a single direction where one person follows the other. And we already noted that graphs represent networks. So this philosophy extends to any social network. However, the difference is it may or may not be directed. For example, on Facebook, if you friend someone, it's a bidirectional relationship. Both people must agree to it, so it's not one way. It would be similar to that first graph where they're both connected and you can move in either direction. You also may notice on LinkedIn, when you connect with someone and then you go to other profiles, it'll say you're a second or third degree connection, and this means you're connected through someone. So you've already created this relationship where you're connected to another person, and then if you follow their connections, you're going to be indirectly connected to someone else. And this is really a key component of graphs. You can follow connections or the edges to reach other nodes, or you might not be directly connected to someone in your social network, but you're indirectly connected to them through your friends or followers. Another great example is the World Wide Web itself. When we have websites, we link to other websites, and they may or may not link back. So this relationship again works in one way. For example, this website may have a link to this website, but this website doesn't link back. However, this website links to other websites, so all the websites are connected through these links. And eventually, it's possible to return to a website you've already visited by following links around. So a website is a node, and then its edges or connections to other websites are the links on the page. But graphs can also represent non-digital things. For example, we can have a network of airports. You can fly directly to an airport, or perhaps you need to take a layover, fly to one airport, and then you can reach your destination. So the flights between airports are the edges, then the airport itself is the node. And then to get to your destination, you have to follow a series of flights to go from one node to the final node. But just like real life, there's many ways to get to your final destination, and your starting destination could be any airport. You might have to go through 2 airports, or you might choose to go through Chicago instead of LA. So this really represents that nonlinear behavior of graphs. And just like airports, using your GPS is going to be the same. You can have many destinations and follow the best possible path to go from the beginning to the end and hit all the places that you want to see in between. And the final example we're going to look at is recommendation systems online. These all use graphs. For example, recommended TV shows or movies on Netflix, or recommended products on Amazon. If 2 users like the same show or movie, and then user A likes another movie, Netflix assumes they have similar interests, and then will also recommend that movie to user B. And the same with buying products. If you're on Amazon and 2 people buy the same item, then Amazon is going to look at other items they bought and recommend that to the other person. Graphs are a very broad data structure. They can be represented in many ways. In fact, we've already seen linked lists and trees, and both of these are just constrained, specific versions of graphs. So now, let's go through some of the key concepts for graphs and understand the different representations that you'll need to know for your interviews. The first is one we've already touched on, and that's the concept of undirected and directed graphs. Undirected graphs mean you can travel from any node in either direction as long as the edge exists. For directed graphs, you can only travel in the direction that the edge specifies. So if the edge exists, you also must check if it's in the direction that you want to go. So for example here, we can go from 1 to 4 and 1 to 3, but we can't go from 1 to 2, but we can go from 2 to 1. So we can only follow the edges in the directions that it specifies. So this changes the way we iterate, the paths we can take, and how we traverse the graph. Another important topic for graphs in interviews is the concept of cyclic and acyclic graphs. A cyclic graph means we have this loop or cycle where you can follow it around and eventually reach a node you've already visited before. So let's say we start at 0, go 0, 1, and then we go 2, 3, 4, 5, and then we reach 1 again, and we reached it without ever backtracking. So we continue to go forward through the graph, but then eventually reach a node that we've already visited. However, with acyclic graphs, we don't have this loop, or we don't have this cycle. So if we start at 0 and follow the edges, we only go outward, and we would never reach a node we've already visited unless we backtrack or follow an edge that we'd already gone through. And the big thing to note with cyclic graphs is that it can cause an infinite loop. So if we got to 1 and went 2, 3, 4, 5, and then reached 1 again, we could continue to follow this loop around and around. So as we learn traversal, we'll see how to handle this, but what you need to do is mark that you've already visited a node or seen this node. And an easy way to do that is just store a flag on the node or use an additional data structure that you just mark as true when you've seen this value. So if we've seen 1, mark as true, traverse to 2, mark as true, visit 3, mark as true, visit 4, mark as true, then we reach 5, mark as true. Then we check if we should visit any of its neighbors or follow an edge. Well, we see it's connected to 1, but because we marked that as visited, we wouldn't continue to traverse, and then we wouldn't end up in this infinite loop. It's also worth noting that nodes in a graph aren't guaranteed to all be connected. So you can have this disconnected graph where they're all part of the same graph, but there aren't paths to all the nodes from a specific group. For example, if your starting node is one of these 3, you couldn't reach either of these 2 other groups in this disconnected graph. So when you're given a graph, it's not guaranteed or even required that all the nodes are either connected directly or even indirectly. We can have these separate clusters of nodes. This is in contrast to a connected graph, which is what we've looked at up to this point, where all the nodes are connected, and there's a path from any starting node to reach any other node in the graph. And finally, we'll look at the concept of a weighted graph, where following a certain edge has a value associated with it. And then, in the interview, you might be told to either maximize or minimize the weight from a starting node to an ending node. And a great practical example of this is your GPS. Let's say you have 3 different locations you want to get to. Well, you don't care about the distance. What you care about is probably the time. So it's going to find the path that has the minimal time to get to your 3 different spots. So all the possible paths aren't equal. There's a best path that minimizes the time to get from point A to point B to point C. So in this graph, let's say we start at node 4 and want to reach node 1, and we want to maximize the weight. So we would look at the possible paths and sum the weights as we follow them. So 23 plus 75 plus 42, that's one possible path. Or we could do 84 plus 39 plus 18, that's another possible path. And we could try all these different paths to go from the start to the end, using the weight of the edge to find the optimal solution. And now, let's understand how we represent graphs. A graph is just a bunch of connected nodes, where a node is an object. This node is going to contain data, and then it's going to have edges, which just represents the nodes that it's connected to. So this will be an array of additional graph node objects. And then we iterate through the graph by just following this edges, and then going to those additional nodes edges as well. So we just continue to iterate through the edges of each node object. It's also very common to represent graphs using other data structures. And 3 of the most common are the adjacency matrix, adjacency list, and edge list. And all 3 of these represent this graph here. The adjacency matrix is a matrix or a 2-dimensional array. And if there's a 1 in a spot, that means there's an edge between 2 nodes. Or if there's a 0, there's not an edge between those 2 nodes. So for the edge between 0 and 1, we see 0, 1 has a 1, which means there's an edge. And 1, 0, there's a 1, so there's an edge. And that represents this edge here. Now let's look at 2 and 4. We see there's an edge between those. So if we go to 2, 4, there's a 1. And 4, 2, there's a 1. And node 4 actually has 3 edges, with 2, 3, and 5. And we see for the row 4, at 2, 3, and 5, there's a 1. And this is true for all the nodes in the graph. The adjacency list is represented by a hash table, where the key is the node value, and then the value for that key is an array of the nodes that it's connected to. So for 0, it has an edge with 1 and 2, 1 and 2, so they appear in its array. With 1, it has an edge with 0, 2, and 3, so 1 has an edge with 0, 2, and 3, so those appear in its array as well. Node 2 has an edge with 0, 1, and 4, 0, 1, and 4, and so on. And this is how we use a hash table to represent a graph, known as an adjacency list. And finally, we have an edge list, which is an array that contains arrays of 2 items. So again, it's a 2-dimensional array. But in this case, the subarrays only contain 2 items, and these items are nodes that are connected. So we have 0, 1 here, which means 0 and 1 have an edge. 0 and 2, 0 and 2 have an edge. Let's go down. We have 5 and 6. 5 and 6 have an edge. 4 and 5. 4 and 5 have an edge. So we represent connected items by including items that have an edge with each other for each of the connected items or edges in the graph. And finally, let's look at one more example. Here's the adjacency list, which is a hash table. Node 0 has edges with 1 and 2. Node 1 has edges with 0 and 3. Node 2 has edges with 0 and 3. Node 3 has edges with 1, 2, and 4. 1, 2, 4. And finally, 4 has an edge with 3. The adjacency matrix uses 1s and 0s to represent edges or not edges, and the rows and columns represent the nodes in the list. So for node 0, it has an edge with 1 and 2, 1 and 2. Node 1 has an edge with 0 and 3, 0, 3. 2 has an edge with 0 and 3. 3 has an edge with 1, 2, and 4. And finally, 4 has an edge with 3. For the edge list, it's an array of arrays, where the arrays inside the array are just 2 items that are connected. So an edge between 0 and 1, an edge between 0 and 2, 1 and 3, 2 and 3, 3 and 4. So these are different ways to represent graphs using other data structures. And finally, we might actually find graphs inside other data structures. So imagine the input is a 2D array. Well, we can actually treat the items inside the array as graphs. So each node can go left, right, up, and down. So even though the input is a 2D array, we can treat the items as nodes. And this is very common to do in interviews, and we have a few questions in the Skilled Dev course that really make sure you understand it thoroughly and can fully handle it in your coding interviews. And finally, let's look at the pros and cons of graphs. They're great at modeling these complex nonlinear relationships. For example, they're perfect at modeling social networks where you have followers or friends. They also handle product recommendations where you can find new products by following products another person liked, and so on. So it's the perfect choice when we have these complex nonlinear relationships of directly and indirectly connected items. The downside to graphs is their scalability. The algorithms are slow, so we only use them when we have these complex relationships. And finally, let's discuss how we see graphs in interviews. You absolutely need to know how to traverse a graph through depth-first search and breadth-first search, and we go through that in the course intensively. You need to understand edge cases for graphs, so an empty graph, a graph with 1 or 2 nodes, graphs that are disconnected, and graphs that have cycles. You need to know both the different representation of graphs, like adjacency matrix, adjacency list, and edge list, or if you're given something like a 2D matrix, you need to know how to traverse inside of it like a graph. and this might not be quite clear now, but it will be as you work through the course. A common interview question is to know how to find the shortest path between nodes. And finally, if you have a directed graph, you should know how to determine if there's a path between two nodes. Thanks everyone, and I'll see you in the next lesson.